space is not empty. It bends, it stretches, and near black holes, it reshapes time itself.
For decades, this sounded impossible. Time slowing down.
But according to Albert Einstein, gravity is not just a force, it is geometry.
And when gravity becomes extreme, time itself begins to curve.
This is called gravitational time dilation. And it is not theory anymore.
Near a black hole, a clock will tick slower than ours.
How do we know? Because we measured the light.
When light climbs out of deep gravity, it loses energy.
That energy loss is measurable, and it reveals time stretching. The stronger the gravity, the slower the clock.
A black hole is gravity pushed to its limit, the ultimate time laboratory. At its boundary, the event horizon, time nearly stops. To a distant observer, objects falling in appear to freeze.
They never quite cross. At least, not from our perspective.
But for the falling observer, time feels normal.
This is the paradox of relativity. Both realities are correct.
Time is not universal. It depends on gravity.
And black holes warp gravity more than anything else we know.
A clock orbiting safely nearby will age slower than Earth.
This has been observed around massive objects, including supermassive black holes.
At the center of our galaxy lies one such object.
A supermassive black hole known as Sagittarius A star.
Stars orbit it at incredible speeds. Their light carries the proof.
As those stars swing close, their light shifts.
That shift confirms Einstein was right. Time slows in stronger gravity.
But Sagittarius AX is only the beginning.
In distant galaxies, we observe matter spiraling inward. Its light tells the same story. As gas accelerates toward the event horizon, time, for that matter, slows.
The closer it gets, the slower its clock would tick.
To us, far away, its motion begins to drag.
This is not an illusion of speed. It is the warping of time. Light escaping this gravity well loses frequency. It becomes redshifted.
That redshift is measurable, and measurement is everything.
Using precision instruments, astronomers tracked these shifts. The results matched relativity.
Instruments on Earth and telescopes in orbit.
Einstein called this effect gravitational time dilation. Near extreme gravity, time doesn't move normally. It stretches, slowing compared to distant observers.
The deeper the gravity well, the greater the time dilation. Near the event horizon, time approaches a standstill. Not zero, but close enough to challenge intuition.
If you could hover just above the horizon, you would age slower than the universe behind you.
Minutes for you, years for distant observers.
This is not science fiction. It is gravitational physics.
Every massive object slows time slightly. Earth does it. The sun does it.
But black holes do it dramatically. They dominate space-time. Their gravity is so intense, even light struggles to escape. and because light carries time information. Its delay reveals the truth. The universe leaves signatures everywhere. You only need to measure them.
Modern astrophysics has become precise enough to detect time itself stretching. And the conclusion is clear. Near black holes, time slows.
But what would it feel like to stand near a black hole?
You wouldn't notice time slowing. Your clock would feel normal.
But far away, the universe would accelerate.
Civilizations could rise and fall, while minutes pass for you. This is the asymmetry of gravity. Time depends on where you stand. The mathematics behind this is precise. Relativity predicts exact dilation factors.
As orbital speed increases, time slows further.
Near light speed, time already bends.
But near a black hole, gravity adds another layer.
Velocity dilation, gravitational dilation combined, they amplify the slowdown.
As gravity intensifies, time near the black hole slows even further. To a distant observer, processes near the event horizon appear to freeze, but locally, nothing feels unusual at all.
When stars orbit close to Sagittarius AMX, their clocks fall behind ours. Their spectral lines shift, exactly as predicted.
This was confirmed using advanced telescopes. Precision measured in fractions of light.
The data did not drift. It matched the equations.
Einstein's space-time is not abstract. It is observable.
Near the event horizon, dilation becomes extreme.
To a distant observer, your signals would slow.
Your voice would deepen. Your movements would lag. Eventually, you would appear frozen in time.
But from your perspective, nothing unusual happens.
You cross the horizon irreversibly.
Wall. No sudden impact. Only gravity. Growing without limit.
Beyond the event horizon, our measurements end.
No signal escapes. No data returns.
But physics does not stop there. Our equations continue.
As gravity intensifies, tidal forces grow extreme.
The difference in gravity between your head and your feet would begin to matter. This is called spaghettification, a stretching of matter itself.
But even here, time continues to behave predictably.
But from the falling observer's perspective, the event horizon is not a visible barrier. There is no sudden wall, no dramatic moment of impact. Time continues to flow normally. But gravity is no longer uniform. The force pulling on their feet is stronger than the force pulling on their head. This difference begins to stretch them, slowly at first, then violently.
This is gravitational time dilation approaching infinity. The equations suggest
Time nearly halts at the boundary, but inside, time flows toward the singularity.
The singularity remains hidden, a region where density becomes infinite.
Here, general relativity reaches its limit,
and quantum physics must take over.
Beyond the horizon, escape is no longer a direction, it's a mathematical impossibility. Space itself is curved so completely inward that the center becomes your only future.
But we know this: time behaves differently there.
every measurement outside the horizon confirms relativity. Even extreme environments obey these rules. The universe is consistent, even when it is violent. Black holes are not cosmic accidents.
They are laboratories. They allow us to test time itself.
At this depth, gravity overwhelms every known force. Density approaches infinity, at least in our current models. And that is where physics, as we understand it, breaks down.
Gravity slows time. The stronger the gravity, the slower it flows.
And near a black hole, time nearly stands still.
Satellites in orbit experience time slightly differently than we do. This effect is tiny, but measurable.
Without correction, GPS systems would fail.
Einstein predicted this too. Even small gravitational differences matter.
On massive scales, like near black holes, the effect is extreme.
Light escaping these giants redshifts and reveals time dilation.
We have observed this with stars orbiting the galactic center.
Their clocks fall behind ours, exactly as predicted.
Time dilation is universal. It scales with gravity.
Closer to a black hole, minutes stretch into hours.
Closer still, seconds stretch into years. This is no longer theoretical. It is measured reality.
Astronomers combine physics, observation, and computation.
The result is precise. Time slows as predicted.
If information truly disappears, it would violate one of the most fundamental laws of quantum physics. But if it survives, we still don't know how.
Black holes are natural laboratories, testing gravity and time. They show us the limits and the possibilities.
In theory, you could witness the universe's future.
Near a black hole, time no longer obeys intuition. Seconds are not equal everywhere. Time depends on gravity.
And the stronger the gravity, the slower it flows. This is Einstein's gift to physics, and the universe confirms it. From Earth to the galactic center, time is fluid, not absolute.
And near black holes, time nearly stands still.
What would it feel like to witness the universe accelerate around you?
Minutes could pass, while centuries unfold elsewhere.
From this vantage, you could see cosmic history in motion.
And yet, your own clock ticks normally.
This is the paradox of relativity. Both perspectives are correct.
Every measurement confirms it. Every observation aligns.
Time is flexible. Gravity dictates its pace.
And black holes are extreme examples. The ultimate laboratories.
They allow us to test physics at the limits, where space and time meet. Observing stars orbiting these giants, we witness time itself in motion.
Their light carries the proof.
Black holes remind us time is not absolute.
Even massive stars, planets, and satellites experience dilation, just less extreme.
On Earth, the effect is measurable. GPS satellites rely on it. Near a black hole, the effect becomes dramatic.
Minutes can stretch into years. Seconds can become centuries.
This is not science fiction. It is physics observed.
We measure it in light, in time, in space itself. The evidence is clear.
Gravity slows everything, including time.
And the stronger the gravity, the more extreme the effect.
Black holes are our guides, teaching us how the universe flows.
They show us the extremes and reveal the fundamental rules.
In essence, time is a river, bending with gravity and near black holes.
That river slows.
Almost to a halt.
Black holes teach us the extremes, but they also inspire thought experiments.
What if we could hover just above the horizon? What would we witness? Time around us would pass normally, but the universe would accelerate.
You could watch stars evolve, witness cosmic events unfold in minutes. Civilizations could rise and fall, while you age only slightly.
This is the ultimate window into the cosmos. A way to see time from a different perspective. But such proximity is perilous. Gravity becomes extreme.
Tidal forces stretch matter, a process called spaghettification. Even light struggles to escape. Everything slows down from a distance. These extreme conditions push physics to its limits.
Yet outside the horizon, we can measure and confirm reality.
Time dilation is not imagination. It is verified, observable, and precise.
Every photon escaping a black hole's gravity well.
This allows us to calculate how much time stretches near massive objects. Stars orbiting Sagittarius A planks provide a natural experiment. Their light tells the story.
We measure the delay. We observe the stretching of time itself.
This is the essence of gravitational physics. The closer the mass, the slower time flows.
And black holes represent the most extreme laboratories.
They show us that time is not absolute. It is flexible, relative, and dictated by gravity.
Even in the quiet of space, time flows differently depending on mass and distance.
For distant observers, those near the black hole appear frozen.
For the traveler, time feels normal.
This dual perspective is the paradox of relativity made visible.
Through observation, we confirm Einstein's vision. And the universe continues to teach. Time is a river.
As we explore the universe, black holes teach us the extremes of reality.
They reveal that time is not uniform. It bends, stretches, and flows with gravity.
For travelers near a black hole, minutes could become years elsewhere.
For distant observers, those close to the horizon appear frozen.
And yet, for the traveler, time feels normal.
Every photon escaping a black hole carries a message about time itself.
We measure these signals and map the flow of time in extreme gravity.
Even the largest black holes follow the rules of relativity. Time slows. It stretches. It bends.
Gravity controls its flow. Mass dictates its pace.
Near the edge of a black hole,
For those far away, the universe continues at its usual rhythm.
Black holes are natural laboratories, testing the very fabric of reality.
They allow us to witness phenomena
we cannot create on Earth.
Time is no longer a constant. It is a river, shaped by gravity.
These cosmic giants remind us the universe is not as we perceive it.
they challenge intuition,
They stretch imagination. And yet, we are only beginning to understand.
Every observation confirms Einstein's vision of relativity. Time is relative. It is a flow, not a constant. And gravity is the ultimate sculptor of time. From Earth to the galactic center, the universe tells the same story. Black holes remind us time is not absolute. And near these cosmic giants, time nearly